So we'll be starting. We have note takers. We don't have Jabber scribes. If please someone could raise his hand, become Jabber scribes. Jabber scribe, please. Jabber scribe. Lou, you're the best. Thank you so much. And so this is the POW non-work group forming BAF about predictable and available wireless. This is an official IETF meeting, so all the best practices that you're very aware of apply here. In particular, BCP 1554 for the code of conduct. So please be amenable to each other, and obviously BCP 79. Which deals with IPR. So if you're aware of IPR, about something which will be discussed today, please let it be known immediately or to the chairs at the end of this meeting. As a reminder, we are relayed on Mitico, meaning that minutes will be taken, presence will be logged, you will be filmed. So when you're actually presenting, please stand on the red cross behind the mic, so people on Mitico will be able to see you. We are taking the minutes on the Etherpad. The link is provided on this page. Even if you don't plan to take minutes, please join the Etherpad. That may help you see what's going on. You may correct names or things that were not taken correctly. And in particular, if you just spoke, please come and check whether your name is captured correctly and whether the ideas that you defended on the mic are also captured correctly. And don't forget, we have blue sheets. So I just asked the front-end people to hold the blue sheets for like 15 minutes because we are used that the member of the groups are not predictable and available. So to cope with that, we'll delay a little bit the distribution of the blue sheets. Then again, Etherpad, Mitico, we have like three presentations which will be done over Mitico. We have a mailing list which is POW. As I will say at the end of this meeting, it won't be the final name for this. So if you have not registered yet, please wait for the end of the meeting for the announcement of the new name for whatever we are doing, which will not be POW. So the surprise is to the end. With this, we have a very, very tight agenda. You will see that the sessions are 5 or 10 minutes each, so we have to rush through them. So that's what I'm doing right now, as you observe. We'll be going through the scope, what we intend to do, what is the general objective of this meeting and of the people in this room. We'll go through a number of use cases. We'll just show you a number of them. There are other use cases which were presented in other venues. For instance, there are use cases in the .NET use case document, which is edited by Ethan here. So please go and visit this document as well. And there are the use cases, very interesting use cases, which were presented at the IEEE for a group that was called RTA at the time for real-time application, in particular use cases in the context of gaming, real-time gaming. So all those use cases in the end will end up in this particular document. But right now, we are just in the process of putting that together. Then, obviously, we invited the groups that were the most related to what we are doing to observe whether we have basically overlays or collisions and make sure that in the end this does not happen and we have original work happening here. Then we go through the technologies, because if you don't have technologies to work on, then there's no point in meeting. But we kind of know that there are a number of technologies that are now showing up for which available and predictable properties can be obtained. And so we'll go through a number of them and see if we can work with them as a working group. Then we'll look at the first drafts which were published under POW. So there are 2 of them. There is a third one which is really under BEER, but which is also of interest for this group. And finally, we'll talk about the next steps, which is mostly the first draft of charter that we can build right now. And well, announcing the name of whatever we are doing next, which will not be power, as I say, and it's still a secret. So, scope of the work. Basically, there was this name around about deterministic networking. It's even in the DETNet acronym. People in the wireless world tend to avoid that term. So we also try to avoid that term in the naming of what we are doing. Basically, by determinism, people in math or physics think about repeatable, predictable activities. And so we extracted what we could really do in wireless networks from that. And what we really care for the use cases that you will see is that you can deliver the packet at an expected time or within an expected boundary, and with enough quality to meet some requirement like mean time between fault. For instance, never miss 4 packets in a row or something like that. So we tried to express those qualities without using the term deterministic, and that's where predictable and available wireless came in. But at the end, it's about machine-to-machine communication it's about very repeatable actions. It's about removing some elasticity so that machines can have automated system using those networks. What we can do in a network like wireless is control the time of emission if we have access to a MAC-PHY which allows for that. Typically, MAC-PHYs like TSCH or FDMA will allow you to control the time of transmission as opposed to CDMA. If you have a technology like that, then you can program when the transmission will happen and you can control the time of delivery. So that's one thing we can do now with some of those technologies, control the time of delivery. What we cannot do is control the delivery ratio, in particular in the ISM band where you have collisions that can come from uncontrolled devices. So we cannot control the delivery ratio, but what we can do is use all the mechanisms that we have at hand on the wireless space to optimize that ratio and avoid many losses in a row in particular. The mitigations depend on the threat. So that's why it takes all forms of diversity, frequency diversity, time diversity, space diversity, beam diversity. There are many forms of diversity, coding diversity, which can actually each in its own way help alleviate the causes of frame loss. So we'll go through that and we'll see the needs to be able to express that as we configure a wireless network. So at the end of the day, everything quote-unquote deterministic boils down to being able to schedule your network and schedule your transmissions. The reason why you schedule is to be able to reserve the resources, make sure you're never out of buffers or bandwidth or anything like that. So it's all about resource reservation in the end. With that, on wired network, and the DETNet experts in this room will tell you that, we can provide a high delivery, we can avoid congestion loss, pretty much what we call congestion loss on wires, which is really collisions inside the device and queues getting full, something like that. We can allow much higher ratios of transmission of critical flows, like the highest QoS can reach 60 to 70% of your traffic. And we deliver within a bounded latencies. That's really the critical aspect of those networks. We can do that because we schedule the network. Those benefits exist in wires. They also exist in wireless. Scheduling provides additional benefits in wireless. One of the key benefits we can obtain is avoiding the gaps of time, such as IFS in CDMA, where there is no transmission. If you schedule every transmission, you know exactly when it happens, and there is no reason to stay silent between transmissions. Critical to IoT and machine-to-machine relays, we can schedule when you send and you receive, meaning that the rest of the time the device can be sleeping. And this is how battery optimization is obtained. If you have to screen the network periodically to see if there is a transmission for you, or if you stay always on, then your battery will deplete rapidly. On the other hand, if you have this IoT device that must live on battery for a year or two, then it must have a very deep sleep schedule where most of the time, 99% of the time, it's not on, meaning it cannot receive any message at that time. So it must be scheduled to know when to receive messages. At the same time, the sender must be scheduled. And if only scheduled transmissions happen and you control most of the emitters, then you can also remove most of the interferences. We can never say all, in particular in the unlicensed bands, but at least we can reduce the interference dramatically if we can tell most of the devices in the network not to send at the time of a scheduled transmission for a deterministic flow. Now, we want to achieve those determinism, quote-unquote deterministic properties. How we can achieve that will have to be different from how we do it on wires. And that's why we're here. We have to understand the particular properties of wireless. We have to leverage those properties and be able to program that into the network, on the multi-hop network, to be able to obtain the capabilities we want on wireless. And a good part of the presentation today will be about understanding what those properties are and see how we can program them into a schedule. So that's the goal for today. Why are we here? We're here to find about radios which could provide the MAC-PHY capabilities that we need to get this end-to-end predictable and available network. We need to understand what must be specified to the intermediate hops in order to take advantage of the special qualities of the radios and enable the high delivery ratio that we're after. And as you know, radio networks are not stable. Things change all the time. You move by a few centimeters, the properties of your radio change. Something in the room moves, the property of your radio change, meaning that you have quote-unquote mobility even if you stay at the same place. The radio link has to be reevaluated all the time, meaning that the routing that you're building on top of it may need to be reevaluated. You can't rebuild your routes every second. So you have to think about separating what you do at the routing level and what you do at the forwarding level. At the routing level, you need to enable many ways to get there. And at the forwarding level, you must decide out of all those possibilities which is the one that gives you the best results at this particular time. This is why OAM, instantaneous understanding of the properties of your path, is so important to us. It's important to DetNet, it's a lot more important to us. We must permanently reevaluate the quality of the possible path that we are using and use the one that works best. If we use too many of them, we are interfering too much with the rest of the world and we are wasting energy. If we don't use enough, we are losing packets. So that needs to be tightly evaluated and recomputed all the time. That cannot be done, from a controller every second. We have to do that at the forwarding time. So that's why OAM is really critical to us. And with this, if we have any question about our scope, this is pretty much where we're going.
János Farkas, I have a question for clarification for my understanding. My read of the previous slide and somewhat this slide is, so are we after to specify the scheduled transmission, like the scheduling part of the radio?
We are at least after specifying what can be scheduled. We'll have to work with the ISG, the other chairs, etc., to decide exactly if there is a data model to be built, in which working group it will be finalized. But at least we are the source for what type of information goes into that data model.
Okay.
Because it's a very special skill, and you'll see that through the presentation today, to understand what can be scheduled and how, and which properties are useful in which radio. And those properties are you'll see on some of the slides, they are not necessarily classical if you're coming only from the wire space.
No, the reason I'm asking is typically part of the media, like thinking of 802, like 802.11, the schedule is controlled by the 802.11 specs, or that's within 802.11 scope. That's my understanding.
Right,
but
and
anyway.
you would see the same from 3GPP, but we can at least probably ask them a certain service, and we'll see how we can do that. But ask for a certain service, and we'll get back from them what we got. Probably they will have to schedule it inside their network for that particular hop, and then we'll have to build a multi-hop network based on that. We don't specify exactly. We'll have to be abstract, right? Because the TSCH is not an OFDMA. we have to do something which works for both. But at least LT and AX, they look very much the same because they're both OFDMA. So we can probably go around that. I mean, an abstract, TDMA, FDMA, that's the beginning of it. And then again, we'll go to the next slide. So that will be the use case. Carlos, if you can come take this mic.
Okay, thank you. I'm Carlos Bernardos from University Carlos III, and I'm presenting this on behalf of my co-authors. So this is basically about to present some use cases for PAO. This presentation is not meant to be exclusive in the sense that there are other few use cases that we are considering already. So these are just some examples to try to provide the motivation for the need of PAO. So for each of the use cases, I will briefly summarize the use case scenario. Then I will try to identify some specifics from that use case that make it different from the others. Then justify a bit the need for wireless in these use cases, although I think it will be pretty clear when we describe the use cases. And then try to identify some specific demands or requirements from each of the use cases for potential work that PAO will be doing. So let's start with the first one. They are listed in no particular order. So the first one is amusement park. So I guess we have an idea of that. We have an attraction park where we have attractions. Those attractions have sensors and actuators that need to provide different data among them and to a potential controller that is in a remote location. We may also have CCTV cameras recording and doing some real-time processing. We may have people wearing wearable devices for identity tracking and all these things. So basically, we have an environment which is large scale and that is composed of multiple types of networks that need to interact among themselves. So this is basically the main specific characteristic of this use case. That is a multi-scale topology. So we have local area networks, for example, for the real-time sensors and actuators. We have wearable devices, and we need to have the connectivity between global systems in the park. So these are kind of specific things of this use case. Why do we need wireless here? Well, I think it's clear. Wireless is cheap. We need a very large area to cover, so this will not be feasible with wired connectivity. Then we also have devices that are mobile, not only in attractions, but by the users themselves, and we need to provide connectivity between many different systems, for example, for maintenance purposes. So we need wireless here. So what do we require from PAO, from this use case? Well, we need to support different kind of traffic, heterogeneous traffic with different criticalities and different requirements. We need to be able to schedule to support IP traffic over a set of different technologies and providing quality of service with different SLAs. So this is basically the main requirement for this use case, which we'll see that is also a common thing that we will see in other use cases. So let's move to a second one. Second one is wireless for industrial applications. Considering, for example, a factory that is manufacturing some kind of goods. So there we have different things, and basically we have a controller that is receiving a process control from the different parts of the factory. So what is specific for this use case? The main difference is that we have two kind of networks or traffic in this case. One that is for the process control. So basically, we need to have this network for controlling the different tools in the factory. And depending on the industry-specific thing, the demand for periodic traffic transmission comes from a few hundreds of milliseconds to just a few milliseconds. But in all the cases, what we need is a flow of packets that is kind of, quote, deterministic, quote, in the sense that the losses and the delay has to be minimized. It shouldn't happen. And then in addition to this, we have also the monitoring and diagnostic network that is basically used to gets data that can be used to optimize the network, for example, using machine learning technologies and these kind of things. And it's important that this network shouldn't be mixed with traffic for this part with the process control loop network. The need for wireless, well, I guess is also clear. There are mobile parts, so wires are not a good tool here. And even if we could use wires, that will be very expensive. And even if we have already a wire infrastructure in place for the control part, for the monitoring part, we need to separate those two networks. So we need to deploy something, and that should be wireless. So what do we need for, what do we demand for POW in this case? So we need to be able to support traffic, legacy traffic, let's say, in addition to the flows that require this predictable treatment. And again, we need to be able to set up a flow with bounded latency between the different points in this case. If we move on to another use case, this is the professional audio and video. For example, we may have announcement speakers and CCTV cameras deployed in transportation systems like train stations, airports, in theme parks. And here, the specific thing is that we need to support uninterrupted stream for the video and for the audio. So in this case, we cannot cope with a network error by retransmitting because we need to have an uninterrupted stream. And another key characteristic is that we need to synchronize the audio and the video with very specific or very constrained requirements. So this is also something specific of this use case. So what do we need wireless? Well, because of the deployment scenarios that this use case considers, needs to deploy different speakers in places, and the deployment consideration make wireless, do require wireless for that kind of deployment for cost reasons, among other things. What do we need from this use case for POW? Well, we need, again, to support different kind of traffics with different kind of QoS requirements. And we need to be able to provide the content with bounded lowest possible latency for the reasons that we saw before, and also to support multipath mainly for resiliency purposes to avoid these network errors that to cope with network errors in a way that we don't need to do any kind of retransmission as we saw before. Then another use case is about UAVs, unmanned aerial vehicles or drones, which are becoming very popular nowadays, and that can be used for many different purposes, like surveillance or even transportation of small goods. And these guys are equipped with different kind of wireless technologies, like cellular or Wi-Fi kind of connectivity, among others. What is specific of this use case? The specific thing is in addition to the connectivity between the guy and the drone and the central control, there may be the need for connection between or among the UAVs for synchronization or for even offloading parts of the computation of a given task among other UAVs that are flying together. The need for wireless, I think, is clear. We cannot wire a UAV, so that's easy. And what will be the specific requests from this use case for POW? Well, we need to be able to automatically or in a self kind of configured way set up the network, because the network itself is composed by the UAVs. So we need to have some kind of self-configuration capabilities. We need to support heterogeneous traffic again, from video to synchronization among different UAVs. And if we are considering this specific case in which we have a service, a function that is decomposed in smaller parts that are hosted by the different UAVs, we need to support the different requirements for the different links between these functions that may be different for the different links that compose a given service. And the last one is the edge robotics control, which is a bit similar in the sense that we have robots that are controlled. The intelligence for managing those robots is controlled at the edge. So we need connectivity between the robots and the intelligence that is managing those robots. So what are the specific things here? Again, we need to be able to support the decomposition of a given service in different pieces that are hosted at different devices, different robots and the edge. And we also need to support very low latency between the connectivity of the robots and the control among the robots themselves to be able to control the robots in a reasonable way. The need for wireless, again, is very easy to see. Mobile devices, do we need wireless? And even if we could wire those robots, the kind of deployment scenarios that we have in mind, for example, in a shopping mall to do cleaning or to deliver some goods, in those cases, we cannot have wires with the robots. So we need to do it wirelessly. So what do we need here? Again, we need to support heterogeneous traffic, types of traffic from the robot to the controller among the robots. And again, if we decompose functions that are run or are collaboratively performed by the robots themselves, we need to support different kind of requirements for the different type of links that we may have in this scenario. So this is a very brief summary of 5 use cases. One key conclusion here is that we have different use cases that do demand different wireless connectivity features, requiring predictability and availability. And these are just some use cases, but there are more. And we are already working on some other use cases, for example, for wireless interactive gaming. This is one example, but there are a few others. So first question would be, should we continue documenting these use cases, additional use cases, and also trying to provide a better characterization of the requirements that each of these use cases poses into the POW potential work? That will be a question for the room. And then, of course, if you have any comments, suggestions, contributions, that would be very much welcome.
Many thanks, Carlos. Do we have a question?
This is Ravi. My question was, because what I understood scope was to come up with some new kind of scheduling mechanisms in the MAC layer. So a lot of these use cases can be covered with 5GNR, I suppose, because it offers you like hundreds of microseconds delays. Has that been considered? Or, are we considering, if it's cellular, probably that would be a choice?
So, I don't know, you want to take it or?
Well, if you're implying that we can do everything with a single hop cellular, the answer would be probably not. We are looking at everything which has to deal with multi-hop networks. If a single hop radio network can do the trick, it's like, if you can do it at layer 2 with TSN, then it might be that .NET doesn't have much to do. Same thing here. If you can do everything with one hop layer 2, then you're happy. You don't need us. But if you're building a network which requires properties over multiple hops, some of them wireless, then probably we need to be able to specify that path end-to-end and provide to the different layer 2s the property that we expect from them for a particular hop, and be able to join the packet from one hop, which is this type of link, to this other hop, which is this other type of link.
So does it include ad hoc networks? Because
no, there is a real difficulty, a real tension between ad hoc mobile in the one hand and quote-unquote determinism on the other. There are things that can be done, and I hope that we'll see drafts about managing a controlled mobility that can still be deterministic. But we certainly will not start with mobility or ad hoc.
Okay, because I thought the UAV use case included a UAV to UAV interaction too, so that becomes an ad hoc.
Yes, and you could say that if in something like a factory or something like that, you have enough control on the mobility of the devices that the network that you form doesn't change too much. If the generic case, is very, very complex problem, because there is this tension between programming, understanding something, and everything moving all the time.
Okay, thank you.
Please go to the notes, make sure your question is well noted and your name is well captured.
Julius Krobacek, may I ask a very naive question, please?
Sure.
There is one thing I've been struggling to understand, not only with you, but in general. So you insisted on the fact that that those are applications in which you cannot deal with packet loss. Now, this is radio, there will be
But we never say
loss.
that.
Well,
no, it's not written anywhere.
Okay, so I would like to know what exactly is the property about packet loss. How do you express the property that you would like?
That will be a very important work for this group, and it will not be expressed in never lose a packet. Even wires don't do that. And the 10 minus blah is usually not very useful either. What's very useful in applications that I'm aware of is more like MTBF, mean time between fault. For instance, if you operate a factory, you've got this control loop, and you lose one packet, it's never a problem because you expect that you will lose one packet. That's part of the game. Now, if you lose 4 packets in a row, then the robot concludes there is a loss of connectivity and it will go to emergency stop. So clearly, the MTBF for this particular case is never 4, right? So this is the way the quality of service that we want to obtain will be probably determined, but it depends on the use case. But for everything automation, machine to machine, it's usually expressed into mean time between fault. And obviously, you've got jitter boundaries, you've got latency boundaries, etc. If you have a control loop which is 100 times per second and your latency is 100 milliseconds, you've got a problem.
Could you give me a slogan to Google?
Sorry, I could not hear that. Could not hear your answer.
Could you please give me something to Google on the subject? What do I throw into Google to learn more about that?
Could you please Google?
What keywords do I put into Google to learn more about this kind of properties that you're expecting?
Okay.
Google is a search engine.
It sounds like you're saying, if you're not losing packets, how can you guarantee that you're going to have the packets all arrive at the end? And my understanding is that in a wired system, redundant paths are optional. But in this kind of system, redundant paths are an absolute given. So it's given that you're going to lose some packets, but it's also given that there's going to be redundancy.
No, my question is not about mechanism. My question is, how do you, if you're claiming to achieve a certain property, how is this property expressed?
Start, keyword to start with, forward error correction. That's not his point.
So,
well, no, that's not your
so
point.
actually, Julius, you're welcome to
dig
come and
into-
write a draft about this because that is a key question. I'm not joking at all. That's a key question. And there is a lot of work that was done in that area like 20, 25 years ago. And starting with acronyms like MTBF will take you a long way to finding these papers. Everything which is expressed in the 10 minus is of not so much interest here because the factory can block with the 10 minus.
Okay, I guess that's a start. Thanks.
Lou Berger with 2 different Jabber questions. So the first, and I'm going to apologize on names right up front because I'm going to get them wrong. The first one is Diego de Hovne. Apparently, I have to eat the mic. Excuse me. I don't know if I can eat the mic and see my screen at the same time. Okay. Which lower layer wireless protocols would you use for mobile applications?
That would be the next slide. Since we are late in time, the answer will come right next.
Okay. And this is from Ahaya Gupta. Are we looking to include vehicle ECU to ECU wireless communications? I'm not talking about V2X/V2V, I guess, well, what does matter? Type of communication, rather intra-vehicle communication.
That's an interesting case. We have not listed it yet in the use cases. I hope we'll be doing that because a large piece of the weight of a car comes from the copper that's used for wiring. A large amount of the complexity of building a car, the cost of building that car, is also all this shape that you have to build where you lay out all the wires. So if some of that could be saved, I mean, you can build waveguides in the doors, for instance. That's something that can be done. But we don't have the use case right now. Hopefully it will come.
David Black wanted to ask about the relationship of this discussion to the deterministic networking use cases draft that's currently at the RFC editor.
In DetNet, we started out having some wireless use cases. Mm-hmm. And in order to simplify or constrain the problem, as we discovered that the ways in which deterministic behavior is implemented in wired versus wireless systems, we decided to split off the wireless piece of it and to handle it separately at some time in the future. And this is nominally that time in the future when we're deciding to actually look at the wireless cases. But in DetNet, we explicitly decided to not deal with the wireless cases.
Okay. Reason for the comment is that some of these use cases are quite reminiscent of the use case draft. It's just what's changed is a decision to use wireless to realize some or all of the solution.
Which is exactly correct, yeah.
Please, we are way ahead of, late in schedule, so let it be very quick now.
Yeah, I think it would be, following on to the previous question, sort of understanding the feasibility of this, because it sounds a bit hard to, even though you have a bunch of diversity, bouncing things off of objects, whatever, right? Guaranteeing that you will never see 4 in a row seems hard. So is there sort of some research that shows the feasibility of this? It would be good to send some pointers to the list of the state of the art there.
There are papers and there are even theses about that, but we never claim never to lose a packet, right?
No, I said 4 in a row. That was your claim. The quality you cited was, I will never lose 4 in a row.
I will never lose what?
4 packets in a row.
Yes, 4 packets in a row, yeah.
Yeah, so that's the, if that...
Well, never is, even that, I mean, if you push that to the chances of 10 minus so much, then, then we're good, right? But the factory should be able to operate for years without ever losing 4 packets in a row. That's kind of the
you put it down in the earthquake category, whatever probabilities you're operating. But so my other question is, and maybe you'll get to that later in case I'll sit down, is sort of what's the intended architecture here? Because is the intended architecture that there will be some sort of ARQ layer that will know about these qualities that you're asking?
The answer is at the end of the slide.
Okay.
Yeah. But yes, it's ARQ on a lot of steroids there.
Alyssa Cooper, just because you said it twice, there, on slide 8 it says losses cannot occur, which might be part of why people are confused. I was definitely confused. So if that's not a requirement, then that might be where it's coming from.
In the slide, maybe I should have put, like Pascal said, but in the draft it's explained that it's about not losing too many packets. The number of 4 is one example. Yeah. Yes, but in the draft is better explained.
I understand from the discussion that probably we'll need a document just to formalize that, at least point on existing art and how you measure the errors, etc. I don't know if that can be done at .NET Common or etc. because you have the same characterizations to make. But I understand it's needed because just claiming 10 minus 5 or 10 minus 10 doesn't help a lot. Okay, and with this we really need to move because now we have lost a lot of time. Not lost, but consumed a lot of time. No, you know you are. So.
Hi, I'm Lou Berger. I'm going to be talking a little bit about DetNet. It's a working group that I co-chair with Janos Farkas here. Turns out I also co-chair traffic engineering, architecture, and signaling working group TEAS, which is somewhat related. So I may bring in a little of that. Next slide, please. Oh, sorry about that. So I'm going to take a step back. This is you can read this or look at the charter, but I'm going to take a step back and just talk about what DetNet is. So DetNet is all about ensuring that we have guaranteed delivery of packets within a guaranteed time window. And guaranteed delivery means we look to mitigate lossy, we want to take advantage of the links that can best support the requirements of a service. So we'll certainly avoid loss in the cases we can avoid loss. Right now we're doing 1+1 protection for those in the transport world, packet replication and elimination for those who don't know that term. And so we're doing redundant traffic delivery. That is what our solution is from an architectural standpoint. DetNet allows for anything, including like network coding. In fact, that's explicitly called out in the architecture document. We also are very concerned about latency, and we calculate the latency across the networks to ensure that packets for a particular service or a particular flow are delivered within the context of that requirement. We are a multi-hop solution. We are just like IP is multi-hop going across multiple subnetwork technologies. That's what DetNet is focused on. I'm sorry to counter the chair about a document that he's an editor on, but we still have wireless in our use case document. Sorry. So it's there multiple times. The difference is we're concerned with what's going on to make a multi-hop network work. We are not concerned at all about how to make a multi-hop RF system work, and that sounds like that's a little bit of what's going on here. So my question turns into, are we looking at a layered approach, sort of standard IP multi-hop networking over some RF subnet where we have clean layering, or are we going to try to do an integrated optimized solution where we try to optimize our IP layer multi-hop networking with an RF multi-hop networking? The analogy I would say is, are we trying to optimize our Ethernet network at the same time we're optimizing our IP network? And I'm asking the question, and I think that's for the group to decide, and maybe today to decide, or tomorrow.
Right. If you just ask me, we are not here to boil the ocean, and if you did not yet at .NET interact with TSN too deeply, I don't see why and how we could try to integrate with the radio layers also.
I have to say the acoustics are terrible here, and I know we're 5 feet apart, but I'm not getting anything.
Okay.
I have weird ears. And
so short answer is trying to integrate deeply with the radio layers would be even more difficult than .NET trying to integrate deeply with TSN. So that would be, for me, boiling the ocean. And that's, for now, what I'm after is pure inheritance from 6-ish and .NET, and just adapting that spawning, really, into the wireless, more specific use cases, like extending in, .NET into that world, benefiting from what you did and pushing it harder for the wireless.
So what I'm hearing, what I would call that is an integrated, not an integrated approach, but more of a layered approach. We do that a lot in the IETF, and I can talk about that in a moment, of how we do that in other working groups, and that's great. That makes a lot more sense to me than trying to optimize, again, talking from the wireline perspective, trying to optimize IP and Ethernet networks together at the same time. So that's actually a really good answer. So let's moving forward. We have a charter. We cover the architecture. We have a data plane definition. We did the hard work on the data plane about a year ago, and we've been having a little trouble documenting it, but we have agreement on what it is. We think we've sort of broken through, and so looking forward to data plane documents kicking out soon. We have an architecture document that's kicking out, so we're making some good progress on those. We right now are stopping at models for control of a DetNet, and so again, a multi-hop network. And so the model of control is stopping at a Yang definition. Whether we do control plane in the future or have other groups do the control plane, we'll figure that out. Let's finish this piece of work and we'll go from there. But again, our charter is the multi-hop network. It is not to dive into the details of a particular network. And there's a parallel here in some other groups, and the reason I mentioned T's I'll say right here. So DetNet fits into basically a family of working groups that are related on different traffic engineering problems. DetNet differs from what we were seeing in MPLS or in T's, is in that it has a much higher delivery requirement than we traditionally need to support in internet technologies, even when we're doing traffic engineering solutions in the internet. So we're going to coordinate with other groups providing solutions. One of the two of them that really matter is this T's working group that I brought together, and CCamp that we'll hear in a moment. T's is worried about the overall architecture. CCamp is worried about the binding of that overall architecture to specific technologies. And maybe that's a parallel here. Maybe that's how we could split things between these two, if we form two groups. Maybe that's how we split it, is you're more about looking at how to map DetNet down to the radio layers, and maybe there's enough there. I don't know.
That's exactly how I see it.
Yeah, so that actually fits in very nicely what we've done in other groups. Yeah, I think there's a lot of coordination that has to happen there. We can talk about, the IESG well understands the coordination, how to make that work, and how we've made it work with T's and CCamp and MPLS and PCE. And I think, I'm not sure now, Spring and Beer, by the way.
it's a lot of fun. One thing we're not working on, we are from the network layer down, and I think maybe that's why we're in the routing area, but we live in the routing area. Certainly transport protocols and above, those are all out of scope. Oh yeah, so I forgot a couple of other. In order to make this all work, there's actually a lot of groups we're coordinating with. There's a list here, eye chart of how we coordinate, but really this is, it really takes the participation of folks in different groups, showing up in different groups and making sure there's good tight coordination, the chairs working well together, and with the support of the IESG. And generally we work out pretty well.
If I may say, you have listed 6-dish here. 6-dish. The point being that 6-dish will not actually work on the .NET piece. It will probably end very soon. And what we do here would be like the spin-off of 6-dish, maybe in more appropriate area to specialize on the interaction with .NET.
Yeah,
so it's not a competition to 6-dish, it's actually the continuation of 6-dish with different means.
Okay. We've had discussions sort of with the chairs, with the AD of envisioning what's going to happen next when we start needing to do control plane, when we start needing to map to different technologies. And what we've viewed is .NET will largely be doing requirements, and then shipping off the details would be happening in the existing working groups that own the protocols. So, for example, there would be work going on in T's if we were going to do a distributed protocol, a distributed control plane, or there would be work in maybe in CCamp after we complete the initial set of mapping of .NET to different technologies. Right now, we're doing that work in .NET, so it's possible that it would continue. What you're suggesting here is breaking off the wireless part into a new group. I see pluses and minuses. I just think we were going to have to really coordinate in order to make that work. But we can talk to each other,
and we do.
Okay, so we have to worry about how we do this coordination, deconflicting in the future. But my understanding is this is a non-working group forming BOF, which means we don't have to talk about it right now.
Right.
So we can worry about that in Montreal. Thanks.
Thank you so much, Lou. And I will ask, who's representing CCamp today? And we are a bit late, so I'm sorry, but I will ask you to...
I'll give you back some time.
Yeah, great.
I know it's always appreciated.
Oh, it is.
So, hello everyone. My name is Daniele Ceccarelli. I'm the co-chair of the CCamp working group. Actually, I'll be very, very quick since Lou already did a very good introduction of all the work that we are doing in this area. No, thanks. So, surprisingly, we didn't coordinate in preparing the slides, but we used the same stack. Different source, but same stack. So you see, this is where this is our comfort zone, the lower layers of the stack. What do we do at that layer? Basically, we standardize control plane and measurement plane for everything that is non-IP. That sits at the lower layer. So we deal with the cross connects, switches, ROADMs, time division multiplexing, Ethernet switches, and yes, wireless. We have recently started working on microwave links. So there could be synergies with what is being discussed in this environment. Talking about the work, what we are focusing on right in these days. Again, extensions to traffic engineering protocols for non-packet technologies. So layer 0, layer 1, layer 2. It's basically what you probably heard under the name of GMPLS. It's a generalized version of MPLS that applies to all non-packet technologies. We do extensions to the IGP protocols, ISIS, SPF, signaling protocols, RSPPT, owned and defined by other working groups. We own the last protocol, LMP, LMP stands for Link Management Protocol. It's a protocol that is used for several purposes, like maintain a control channel connectivity. So this is not something multi-op or end-to-end. This is specific to a single link. It is used to verify the physical connectivity of the data links, correlate the link property, and suppress downstream alarms. And then Yang, a lot of models, as everyone is doing in the routing area and everywhere. And SDN, yes, we deal also with SDN. There is a lot of work, a lot of architectures being defined in the various areas. For example, in TIS, there is a work known as ACTN. We do this technology-specific extensions for ACTN, like defining the Yang models needed for management and control of optical trails, microwave links, etc., etc. Fast enough?
Oh, that's perfect. Thank you so much. And with this, we'll give the ball to the...
Yes, on this slide that you just showed, my name is Charlie Perkins. You showed some interesting things that you want to monitor and measure about links. Do you think that your techniques are... Do you think that on the slide that you showed, you were making measurements for various properties of the links? Are those techniques in CCAMP applicable to wireless links?
Microwave is on.
Oh, the previous chair of the CCAMP.
Yeah, actually, you're going through here. This is Lou Berger, sorry. You're going through here, and it occurred to me I left something off. The MANE working group is working on a protocol called DLAP. And I actually ended up doing some work on DLAP because I worked on LMP, and DLAP is LMP for wireless networks because they didn't know about LMP at the time. LMP, and I think this answers Charlie's question, LMP could have been extended to be DLAP, but it happened in parallel and it was too late to sort of say switch over to LMP. So we have LMP for wired optical networks and DLAP for wireless networks. They do the same thing. They, of course, provide different information.
More coordination headaches for you.
Right, so that's what happens when we don't coordinate, by the way. We end up with two protocols for two different target markets. Even one would have been fine.
And DLAP will be of high interest, I guess, for SPARM. Yeah, but it applies to way beyond MANE. I mean, and this is me. So I try to give myself some time. So now 6-ish co-chair hat on. So 802.15.4 time-slotted channel hopping provides you with this nice matrix of time and frequency, and you can allocate resources, a given square there being the time just to send a packet and get an acknowledgement back. And you see that you can allocate a particular of those resources to a particular transmission. You could use that, and some industrial protocols use that for quote-unquote deterministic properties. What we've done at 6-ish was consider the other side of that net. The dark side of that net is that on the same network, you must still be capable of operating stochastic IP, best effort IP. So what 6-ish has done so far, and what it was intending to do, was to enable IPv6 on the slots that you can see there that the deterministic flows would not be using. How to be elastic, how to adapt to traffic, which is non-deterministic. And 6-ish has been doing that, and we are very close to completing our charter and terminating the working group. What 6-ish also did is write quote-unquote, not quote-unquote, write an architecture that details both the stochastic traffic and the deterministic traffic. And based on that architecture, promote some work at .NET. I mean, we wrote a 6-ish for .NET or .NET for 6-ish, I don't remember which order, document explaining to .NET what the requirements would be from our standpoint to enable determinism on the TSCH network. But as Lou said, I mean, and as Ethan said, the wireless is not the first priority for DetNets, though we wanted, and we still want, to completely inherit the DetNet architecture for wireless. We also needed, and that's what we expressed there, to be able to configure something maybe more complex, something different, which would be the wireless network. So that's where we are. On the one hand, we've enabled classical IP, stochastic IP. On a deterministic MAC, that's TSCH. We know how to avoid collisions between deterministic and non-deterministic. But 6TiSCH has done nothing and will do nothing about the deterministic side of it. How to apply DetNet on that TSCH network. And that's pretty much for a number of good reasons. One of them is wrong area. One of them is wrong people in the room. We wanted to defocus from TSCH and maybe take a more global view on more wireless network. Now we've got an architecture that works on TSCH. Maybe generalize it a little bit and inherit from both the TSCH architecture and the DetNet architecture, and to make something which is consistent between the two. And that's pretty much why we're here. We are trying to build this hybrid between 6TiSCH, which really did the stochastic part, and DetNet, which explains a more general way of how to do deterministic. But we need it more specialized to our problem. And that's pretty much why we're here. And any question? Any question on 6TiSCH? So we'll have more later about the TSCH, etc., with Xavi, so I'm not consuming our time on this now. And with this, we're going to have
Can I ask one question?
Yes.
So I just wanted to understand.
Can you speak your name again, please?
Yeah, Ravi here. Just wanted to understand the application, the workloads you're considering here, because the scenarios that you said consider has audio, video kind of applications, and 15.4, what I understand, is like 100 to probably 300 or 400 kilobits per second kind of mediums. Are you considering high bandwidth applications or?
Okay, so I'm not sure. I didn't get all the words because the mic is and the acoustics in this room.
What I'm trying to say, are you still considering the case of constrained networks? Are you considering ones that is which has fully functional devices with high bandwidth links?
So TSCH is not constrained to FFDs, to fully functional devices. It is operating on a 15.4 network with any kind of devices. But you need to have this MAC layer extension over the 15.4 MAC, which enables to understand timing, so to synchronize, and to understand schedule. So this is it used to be 15.4E, and 6TiSCH operates on that. Now it's all wrapped up right back into 15.4 2015, but we operate on that. It's obviously a constrained network because 802.15.4, and usually very slow, like in the minimal.
Yeah. No, because it kind of conflicts with the use cases that was presented. It said audio, video, so it's not for transmitting videos for sure, right? You're still doing probably sensor network kind of things.
TSCH is sensor network. It's process control.
Yeah,
it's supposed factory automation for robots and movement detections. You don't do that with TSCH. But we can do long distance, and that's also appreciated too. And the real point of doing IPv6 over that was to enable diagnostics. All the backend data that cannot interfere with the control loops, and that still need to be carried on the same network.
Yeah, I understand. Some of the use cases seemed conflicting with what the radio was. So
it was part of the industrial, but for process control, I'd say.
What Carlos presented had audio, video as one of the use cases. Right.
Carlos Bernardo, yes, but in these use cases, we are not restricted to one particular radio technology, right? So it may be others, so it's not only for that one.
So you will have different radios for different needs. Factory automation will not be on 15.4, but process control is usually.
All right, this is from Mina Raddy on Jabber. Concerning spatial reuse of channels in the mesh, are you assuming a certain spatial organization of the mesh, i.e., not just a randomly distributed mesh?
No, we are not assuming that. Actually, the art of what we are doing does not really does not centralize the allocation of channels, right? So it's all found dynamically by screening the air. So we don't assume anything. We just look up for time slots which are not being used in our area, and we allocate them for peer-to-peer communication. That's what 6TiSH does. But 6TiSH is not centrally controlled. It's distributed.
Okay, Pascal. So one question. So in 6TiSH, we just do hop by hop. So you mean one of the motivation to have POE is to have the centralized routing and scheduling, right?
Exactly.
Okay, thank you.
And Remy, did you state your name? I mean, I'm not sure if the... Oh, please check on the notes that your name is captured correctly.
Lou Berger for myself. So what you just talked about was what 6TiSH does. Can you clarify what you expect this group to do?
Well, we expect this group to complete the dot of the 6TiSH architecture. The 6TiSH architecture describes stochastic and deterministic flows, but the working group only worked on stochastic flows and expected to inherit from the work in DetNet for the deterministic flows. And as we think about that, we realize that probably it's better to disband 6TiSH and form a new working group for doing that piece, as opposed to hosting it in 6TiSH, which was not really meant for it.
Again, Lou, I think it would be worthwhile at some point to clarify if this is just going to be deterministic networks for 6TiSH or deterministic networks over any wireless network.
That's probably the next presentations.
Thank you.
It would be too constrained for a working group probably to just focus on one technology. Now we know where we're going. So the goal here is, one of the reasons why 6TiSH is not appropriate is we want to extend to more radios. And so with this, we'll start with the first of those radios, which are non-TSCH. And that will be 802.11 extreme high throughput. I hope we have Dave here. Dave, I can't see you. Dave, can you try to join the Mitico? Why is it that I'm not seeing Dave? Dave, are you here? You should see him on the Mitico. So Dave appears on the list, but I'm not. Normally there should be this guy moving here. You must press something, Dave, to ask for the mic, right? Okay. So yes, we'll move on to the next one. And that would be Bikram. Sorry? Yes. Dave, do you know how to enter the queue? I thought you rehearsed that. Okay, we'll ask Bikram to present during that time. Dave, please check how you do that and make sure that you can enter the queue. That's exactly what we are doing. So it's going to be ultra-reliable low latency in 5G with Bikram.
Okay, hello everybody. I'm Bikram from Ericsson, and my background is not from here, IETF. I'm work for 3GPP and precisely working on protocol design in the physical layer and focusing on URLC, or I would say grant-free technologies in the URLC. So I'll give a brief preview on URLC and how we can exploit URLC communication for deterministic access. So let's begin. First I talk use cases and the requirements. 3GPP has analyzed various use cases, for example, smart grid or mobile robots, etc. And they require reliability from 3 nines to 5 nines, even beyond. And low latency, for example, boils down to 0.5 millisecond or 1 millisecond. And currently, LTE, we do not have this capability. For example, they are built to serve traffic or with a block error rate of 10%, or I would say the reliability around 90%. So clearly we need something which can serve with extreme reliability and low latency. Therefore, we began working with the new radio, which is called NR, 5G NR. Release 15 already been done, and now we are working with release 16. So in release 15, we targeted the reliability of 5 nines and latency of 0.5 millisecond in either direction, uplink or downlink, which is from, well, you can say RLC MAC ingress and egress points. And after completion in 18, we are working with release 16, and we have the same targets. And okay, we increase the reliability to further to 6 nines. And so I will next give a lot of reliability or latency features, which are in 15 or 16. Some are already standardized, some are on the table. So in this slide, I have some low latency features. I will just go through a few of them. First is numerology. And here from legacy 1 millisecond 4G TTI, we able to scale the TTI duration, this transmission time interval or time slot, to further 0.06 to 5 millisecond. So a lot of latency we can save with the numerology adoption. And next is grant free. In the grant free, whenever you have data to transmit, user has data to transmit, it transmits readily on the pre-allocated resource. So it means it bypasses all the scheduling request, signaling related to scheduling requests. For example, in uplink, you have this scheduling request, then grant, then buffer status report, then further actual grant where the transmission happens. So if we adopt grant feed, so we can bypass all this for signaling and user transmit readily on this pre-allocated resource. Similarly, we can mirror the same concept in the downlink as well, but downlink is more easy or flexible in the sense G0B or the base station controls the transmission. Uplink is a bit critical. Another concept is preemption. As we know, in a new release, new radio, we have range of services. So that means the traffic can be critical or non-critical. So there's an interaction between these mixed services. So if the resource is allocated to, let's say, non-critical service, and we have to serve some or cater reliable or critical service, so what do? If there's no available resource, so we can interrupt the non-critical service. So we can puncture that service and put URLC data, which is a critical one. And in subsequent TTI, for example, in the downlink, we can send the indication, okay, such and such services has been interrupted. So another technique, and it also saves latency because we need not to wait for the free up resource in the future. We just do it readily. Fast hard processes here we have. LTE 4G follows the rule of N+4. Every subsequent signaling is done after 4 slots, sort of. And now we can do the DCI or downlink transmission or even the feedback within practically in the same slot. So there are some more features, I will not go through. So in this slide, there are some reliability features are discussed. We have robust data control channels now. Now we have a lower code rate, so that means they are less prone to errors, channel errors, so which increase the reliability of the transmission. Then we have antenna techniques. We have more bandwidth, millimeter wave, extra, and then further, let's say in 4G we have, I think, 8 ports for the beamforming. Now we have 12, so upgradation from those techniques. Automatic repetition, we can use repetition in downlink and uplink for the reliability, increases the success probability. And PDCP duplication in this layer, this is above RLC, MAC, RLC, PDCP layer. And in this layer, now we can duplicate the packet. So it's the same data, but even it may carry different hard processes. So it's sort of like provides reliability to URLC communication. And support for time-sensitive networking. So it has, TSN has, let's say, two features, tracking features. One is reliable deterministic flow. So we can say all those features presented in these slides, low latency or high reliability, we can use that to exploit or provide the deterministic scheduling. Second is accurate time delivery. So right now we are discussing, okay, we shouldn't have jitter no more than 1 microsecond, or the clock information should arrive with that accuracy. In 3GPP, different RAN groups working on different problem related to the clock accuracy. For example, in my group, RAN 1, we are analyzing the clock accuracy over there or over the UU interface between UE and G node B. So we can say that for a cell site of less than 10 meter, we can provide accuracy of around something less than 500 or 400 nanosecond. So clearly, RAN 2 group is working with RRC related accuracy, and RAN 3 is working between TSN Grandmaster Clock and the G node B. So different groups are working on different paths, and they are analyzing the accuracy. So clearly, work is going on, and accordingly, the interaction is going on, and the proposal are being made. So how we do deterministic scheduling or periodic scheduling here? So as I discussed in uplink, we have a grant free. So due to grant free, there's a concept adopted in uplink is configured grant. So in the configured grant, we say in the uplink that we can pre-allocate the resources, and whenever the user has a data, it can transmit readily in a grant free manner. For example, in this figure, in the uplink case, so you have a period here which can be emulated to the latency budget. So in that latency budget, here we allocated 4 transmission opportunities. So whenever a user has a data to transmit, for example, it can transmit on these 4 transmission opportunities. By 4 transmission opportunities means 4 repetition for reliability. So in this way, user can have a reliable uplink transmission for the critical data. And this transmission can go, repetition can go up to 16, depending on how critical is your traffic. Further, we have a multiple configured grants, and if your traffic is a bit fluctuating, so you can adopt, one of the configured grant. Okay, for example, I'm supposed to transmit in the, let's say, the CG1, but somehow my traffic fluctuated and came a bit late, so I can transmit in the CG2. So it's a robust feature again, adding the more reliability. Next is downlink. Okay, uplink is, as I said, more critical. So, because user has to do a lot of schedule, this kind of, okay, so I'll just do fast. Okay, in the downlink, we have this SPS. So these are on the table, like we can reduce the period, and further we can have multiple SPS again for the robust scheduling or deterministic scheduling. So this is summary. We are done with release 15. Now we are working on release 16. Study items are finished. We have some focus problem in release 16. And for the deterministic scheduling, uplink configured grant can be considered as a baseline in uplink. And similarly, we have it downlink, multiple SPS or downlink SPS. TSN capabilities, we are analyzing both deterministic flow as well as the accurate clock information delivery. Thank you.
Thank you very much, Bikram.
So any questions?
Okay, so we'll hurry up because we are getting late. But thanks so much; it's really appreciated. And we see that we see where we should be already on this picture, where you see that TSN is talking to 5G without going through that net, and that's kind of it's time to look at that. Well, to see if we can do something at layer 3 to generalize this interconnection of end-to-end deterministic flows. No, Corinna, it's not you. It's going to be Dave first.
Pascal, this is Lou again. I was actually going to ask a question. But you brought it up, so I'll go there. The interesting thing is they're not talking about doing any network level coding or network FEC. And presumably that's because they're solving it at the lower layer, at the layer 1. But if we're looking at a sort of a multi-hop network, we may say that the best way across multiple hops, so not across a single subnet, but across the N subnets, that we really need to introduce something that's different than the simple 1+1 and really look at network coding. And so that might be something for a future group that we could look at here.
Okay. Was that captured in the minutes? Oh, Luke, can you please make sure that what you just said is well captured in the minutes? That's very important. So with this, we'll invite Dave. And that will be extremized throughput .11. And Dave, I can move the slides for you. We can't hear you, Dave. Did you mute your mic? Oh, Dave's gone. Please join again, Dave. You're there, we can't hear you. Damn. Something must be muted somewhere.
Diego says technical problem on his side. They are working with him, so postpone it again.
Yes, we'll ask Corina. So let's try Dave, and after that it's Corina. Okay, so that's going to be Corina.
Hello.
Hello, Corina. I'm just prompting your slides. We can start already. Go ahead.
Okay.
That's me to move the slides.
Thank you. Thank you very much to host me remotely. As mentioned in the first talk about the use cases, it was said that we look on different ones. So here comes another one. It's on the aeronautic communications, short LDAC. So next slide, please. Next.
Maybe
it is. Okay, I didn't saw it. Sorry. So the global traffic in the air becomes more and more complex, and the problem is that the base stations want to have control over all communications happen between the planes as well as the ground stations, and also manage the air traffic in all phases of the flight. So currently there are many developments ongoing to modernize the air traffic management for civil aviation and transitions from analog to digital communications. Just some buzzwords is the CESAR and the next gen that's looking on that. And the DLR, the German Aerospace Center, hooks up on this idea and now develops LDACs. Next slide, please. The idea is that it's a report already indicated that there will be more and more traffic in the air, and the currently available bandwidth with the communication between the different planes in the frequency band are already very full. So they are looking for new frequencies or bands to communicate there, and also the data is not only with the data that's communicating like the local position, but also coming up more and more requests for videos, for example, to analyze, for example, weather conditions. Next slide, please. So in this, the LDACs solution comes in, standing for L-band Digital Aeronautic Communication Systems, and LDACs will provide a solution that goes on all communication ways, so between the different planes, between different planes and the satellite, as well as ground stations and within the airport surroundings. Next slide, please. Here is a basic architecture described on the slide. So you can see that we have different communications. On the one hand, when the plane comes in, we need to have information to the ground station at the airport, as well as when the plane leaves, we have to do the communication way backwards, as well as the different planes have to communicate with each other, and there they are using ground station, where the information is then sent to a central point, to a controller, which then forwards the different communication to the airport spaces, so to say, and from there the communication is further handled. More details on this are already published, so at the end of the presentation you can see a whole list of publications going on that topic already, so I save some time here. Next slide, please. The main characteristics of LDACs can be seen here summarized in the slide. So the total airspace is separated in different cells. Some cells are overlapping, but it might be, when you're looking here on the picture, that a blue cell is, for example, not linked to a purple cell directly. So we have to have different hops, and in there comes in the mobile stations, as you can see on the right side of the picture. So the plane itself tries to multicast information. So at the end, the final information goes to the ground station. So we have, on the one hand, a rudimentary, basic, centralized communication in place when we just look on the ground station. But as the planes are mobile, we also have to look on a decentralized approach. So the idea of LDACs is to combine both schemes. Next slide, please. And combining both schemes is challenging because, as we all know, also due to the 5G auction at the moment, there are already reserved bandwidth and frequencies. So LDACs looks for a new space to communicate, and here you can see the different frequencies they plan to go on. So we have a special bandwidth available. Modulation is planned, as well as setting thresholds for minimum data rate and maximum data rate. And with this boundary, the DLR is already able to send small data packets as well as long packages, including videos, for example. Next slide, please. And this just came in yesterday, so they successfully launched the prototype LDACs and did the first flight successfully. So as you can see, I'm not talking about theory. We already have it deployed, and now we're looking for standardization here. And next slide, please. Submarine LDACs, it's important for POR because we are looking on another use case, looking in the aerospace. And as you know, there we have different settings for the communication compared to the other introduced use cases. So we also have to think about secure communication, because it makes no sense that the data is transported but might be eavesdropped or something else. So it's really high risk if data is malicious here. And the other thing is we need to have the regulatory organs on board, because the DLR got the contract from the NATO to have it globally acceptable. And finally, I must say, as I'm running out of time and we are already behind schedule, I presented here a slide. Next slide, Pascal, please, where you can find further information about details that are already published, and currently we are working on a draft for the planned working group. Thanks.
Many thanks, Corina.
Hey, Pascal, can you hear me now?
Yes, Dave, I will show up. We'll show your presentation, and you're already there. Okay,
Sorry
thank you,
about
Corina.
that. Here.
Welcome.
And I will press the button for Dave, and hopefully that joins you in. And I see Travis behind. Okay, great.
All right, great. Thanks. I'll try to be quick here, and thanks for the invitation to join this group. So I'll give an update on the support for time-sensitive applications in Azure 2.11. You can go to the next slide. So as everyone knows, right, traditionally Wi-Fi has been focusing on increasing throughput, capacity, and efficiency. But more recently, a lot of the new applications are requiring more than just high throughput, in terms of a low latency, higher reliability, and time synchronization. And this has been recognized within the 2.11 group. And some work has already been done, and more work is ongoing in enabling these applications, within 8.11. I will talk about two main efforts there. One is 11AX, which provides mechanisms to control latency and increase reliability. And the new next generation Wi-Fi standard, which will be called 11BE, or extreme high throughput, which will come after 11AX, which just starting. Can you go to the next one, please? So 11AX brings a new capability to 802.11, which is a multi-user OFDMA. So one of the main issues with the Wi-Fi MAC, right, as you know, based on CSMA, is the contention, right? And most of the time, the delay actually is very low on average, but the problem is in the worst case, in case of congestion, the delay can increase due to contention. And with this capability now in 11AX, which is multi-user FDMA and trigger-based access, it enables the access point to control the access to the network, right, using scheduling. And this is what we've been talking about in this group, and that's why we see a good connection to Wi-Fi being one of the technology that can be considered as well. And as is shown here, now with the OFDMA capability, you can schedule multiple users at the same time, and you can avoid the EDCA contention. And there are other features also that enables the AP to allocate the better resource unit and agree with different stations on times that they can be active or not. That's something called TWT. So combined, these features gives a more centralized scheduling capability to Wi-Fi, which can avoid a lot of the random access delays, right? And I think in a managed environment, this can already be used to support low latency with high reliability. In the next slides, we show an example. If you go to the next one, Pascal. Okay, so this is a very simple example to show the difference in what OFDMA can help. So if you have, for example, 9 users and you have to transmit all of them in time domain, right? They all have to contend for access. It's going to take a certain amount of time. If you have each one of them is going to have to contend, but with OFDMA, you can actually pack all of them in a single PPDU. And of course, the number of users you can support depends on the channel available. But in Wi-Fi, you can go from 20 megahertz all the way up to 160 megahertz. So your capacity can be adjusted as well. But the amount of time required is significantly less in terms of 700 microseconds for 9 users compared to 1.3 milliseconds if you have to do it in the, let's say, legacy Wi-Fi way. So that's one of the capabilities that we believe is very important for these low latency applications. But there are improvements that can be done here, to reduce the latency, even increase reliability, redundancy. And this is actually starting already in .11 with the work in the new group. The next slide, please. So in the March meeting, the working group approved a new project. It's going to be called Task Group B, and the study group was called EHT, Extreme High Throughput. And there was a subgroup that focused on a RTA interest group that focused only on looking at the real-time or time-sensitive applications, as I list some of them here. I think some of those were discussed previously today, so I won't go into the details. But this group looked into, documented all of these applications, and there is a report that can be accessed and look at the different requirements. And in the next slide, I show the summary. I think one highlight here is that you see different applications have different latency or reliability requirements. But one of the fundamental problems that needs to be addressed in the .11 is the need to bound the latency, basically, to address the worst case latency and jitter. And this has been included now in the scope of the next generation, which is the 11B project. And the next one. So, and these are some of the topics that are started to be discussed already and considered in the new 11BE. First one is extension of TSN capabilities. Actually, in .11, there is already support for some TSN capabilities, right? There is support for time synchronization. As was discussed earlier, for example, 5G is trying to enable that. So this is something that in .11, it's already standardized and available. Also, .11 is actually an 802 network. So the interface with the Ethernet TSN is natural, is already there. So there are amendments like .11AK that enables that in the past already. What the group is focusing now are on the features to address the latency and the reliability of the links. And there will be some enhancements for more predictable medium access, reduction of file overhead, especially for small packets, and management of time-sensitive and best effort coexistence and across multiple APs and multiple BSSs. So those are the topics that are being now considered in the next generation 11B. And yeah, so this is a short summary. If you are interested, we can follow up with details and what results have been already discussed. But the main message here is with 11AX, there are already capabilities that you can control the latency, especially if you are in a managed network, like an industrial network, for example. And 11BE is going to improve not just the throughput, but also reduce the worst case latency and jitter and have improved reliability over 11AX. So it's going to take even further. And this work has started in IEEE. Okay, that's it. Thank you.
Yep. Many thanks. We are running late, so we'll move to Xavi very rapidly, but that was great. I mean, that's exactly what I hoped it would be. And with this, Xavi will talk about 802.15.4 TSCH and what we've done at 6TiSCH as well. Xavi, we see you actually.
Hello, you hear me well?
Yes, we do. Great.
Okay, thank you very much. What I would do is I will introduce a little bit 6TiSCH and 15.4 TSCH, although Pascal already did that. But I will focus
a little bit away from your, just a little bit,
but I will focus on the aspects that has not been addressed by the drafts published or presented at 6TiSCH, but some of the topics that are described in the architecture. So next slide, please. The presentation, I will give this overview. I will talk about the concept that is label switching on 6TiSCH, and this is something that we already talked during today in this work group, in these both presentations. And we'll also talk about what are the tracks according to the 6TiSCH architecture. Next slide. So as some of you may know, time synchronized channel hopping is an amendment of 15.4 that was presented in 2012 and then standardized in 2015. And what provides is a schedule where we can allocate resources for the communication between nodes in a mesh network, and we can have multiple trade-off through the allocation of resources in this schedule. for example, tune it for latency or tune it for robustness, adding redundancy in the links, or also to optimize for the amount of traffic or bandwidth that a node requires. So a slot is one of these cells, and inside the slot there's different things that happen, but one of them is that each packet is acknowledged. This means that the inner MAC layer properties provide this reliability, at least for the confirmation of the packets. There are other options provided also by 15.4 that enable retransmissions. So this IRQ that is described in the 6T architecture is possible thanks to the already defined properties of this MAC layer. The next slide, Pascal. So 6T took that MAC layer and aimed to integrate it into the IETF 6LoWPAN and IPv6 stack.
Can you
So
move
there
the
were
mic a little bit closer this time? Yeah.
Yeah. So there were several missing gaps, especially in the management plane orchestration, because 15.4 is not defining a bootstrap mechanism, is not defining a secure join procedure, is not defining how the cells in the schedule are managed, nor what is the policy to allocate them. So 6T took all these requirements and developed, let's say, as Pascal said, a stochastic solution to deal with at least the common traffic in such a networks. But the work at 6T didn't address determinism, how determinism along a multi-path, a multi-hop path is ensured, and how this schedule is done in a coherent way along the path. Yeah. So this technology, and this is a work I worked personally some years ago. This technology TSCH is very well suited to support the concept of label switching, and especially the GMPLS vision of label switching, because it enables to forward packets based on implicit labels. So I give a very simple example here. If I'm node B in this graph, and I want to relay packets that come from node A, the only thing I need to know is that I have to output any packet coming in my cell or slot number 0 through the slot or cell number 1. And this is an implicit knowledge that can be distributed, that can be configured at the nodes in the multi-hop network without having to transport any information in the packet. This is relevant for 6T because we are addressing a constrained scenario where we have only 127 bytes payload. Following that idea, and the 6T architecture introduces the term of a track, which I think is well known.
Actually, can you move the mic again? It's kind of going down and the voice disappears.
Yeah. So I think it's a well-known thing. So it's a determined sequence of cells along a multi-hop path, and it's usually as a result of a reservation conducted by a protocol such as a label distribution protocol or RSVP like protocol. So usually these tracks can have an owner, which is the initiator, and it can be uplink or downlink, and they can be identified in many ways. And from here, we can start playing a lot of tricks in the network to ensure, for example, that we have redundancy on the tracks, so we can add extra levels of reliability into the network. And as a final slide, this is just an illustration of what we understand in 6T for track switching or label switching over 15.4 TSCH, which is basically forward the 6-top layer, which is the management layer over TSCH designed by 6T, all the packets that arrive into a node and are not for that node. And this, of course, avoids a lot of overhead on the processing of the packets, because we are acting at the layer 2 forwarders, as in MPLS. And I think that's my introduction. I'm not sure if you have any other question about this.
Thank you very much, Chevy. Just as a 60th chair, just to be very specific, we defined all this at the architecture level. So these are kind of our requirements, but we never, as a working group, implemented any of the protocols that would be needed to achieve this. And that's when we actually went to .NET and said, oh, how can we work together on making that happen? And that's why we are in this room now. Thank you very much, Chevy. And the next winner is for Tish, and that's going to be me. And we have Lou.
Hi, it's Lou again. Now I'm completely confused.
Sorry?
Now I'm completely confused.
Oh.
I thought we were here talking about, is going to be about mapping .NET to various wireless technologies. And I thought,
Yes,
I thought I understood. The last sentence you just said is we're here to make it so that we build a control plane for 6-dish.
Well, no, it's a use case. Oh, not a use case. It's one of the radios. The interesting thing with 6-dish is that it is already considering multi-hop, which the others did not present to you. They are hub and spoke. So for 6-dish, we might want to provide not just one hop, but multi-hop scheduling.
So if I translate that, I think what you're saying is you'd like to solve the general problem for .NET over arbitrary wireless network, and you'd like to reuse that solution to solve 6-dish multi-hop.
Yes. 6-dish is one of the users of what we are building.
Okay.
But compared to the others, it's the only one which presents it as a mesh problem. So multi-hop. But otherwise, you still have the same FDMA, TDMA kind of structure. I mean, there are many things in common. And so actually, to continue on the discussion, and I will go to the mic here. That's probably, your question is probably a good introduction to what I wanted to say here. So what is kind of specific, how do we need .NET to be kind of extended? What can we, how can we use .NET as it already stands, and what needs to be extended to what .NET already describes in its architecture, so as to solve the kind of problems that Xavi has just presented. So just to reuse the same designs, a traditional forwarding operation would be you've got two nodes A and B that send packet to node X at different times on different channels, and then on different time, different channels, X would forward them to Y, and then Y would forward to U and V. But this model, which is the traditional forwarding model, is not necessarily the way radio networks will operate for us. So the first thing that may happen on a radio network would be the traditional, quote unquote, and that's the inheritance from .NET replication game. So we would have one time slot, channel offset, frequency offset, on which this node G would receive a packet from ingress I, and we see that we can schedule two times, two frequency and time, where G would actually forward to E and F, right? One thing we didn't say about SCH is we are not using this as fixed channels. We are rotating that all the time. So we have a channel frequency diversity because we recompute what you see in this matrix into a real frequency based on time. So it's not directly frequencies, don't think like that. Second operation, which is also inherited from .NET, would be the elimination operation, whereby we've got two different time slots for which we can receive, quote unquote, the same packet. And then we would only forward it once because it was actually two chances to get the same packet from two different paths. Now we get into more unusual operations. One of them is overhearing, and we'll have Georgios talk about that a little bit later. But there is one interesting aspect of the radio. In the one hand, it's lossy, right? You don't have the same kind of delivery ratios, mostly in the ASM band, in unlicensed. But on the other hand, you've got interesting properties like it's often used as a broadcast medium. Unless you do tight beamforming, you have a good chance that there will be more than one device on your mesh that is capable of receiving a packet when it's being emitted. So the first operation that we might have to program schedule into our network is this overhearing mechanism, whereby G sends the packet, broadcasts in the air, and actually F and H are both programmed to capture that packet. Another game which is harder to do, but there are papers which do that, and I've seen that also in the plans for 5G, so Bikram might tell us about that. But constructive interference is the way to send very tightly synchronized packets from two different sources so that the way those two transmissions interfere at the receiver are actually constructive, meaning that the receiver will get more energy, and so it can receive the packet even if it's farther along and too far to be reached by any individual I or E. That's a cool way to work at the border of two cells, if you like. Something which is very usual on wireless, but completely unusual on wires is plain ARQ. That's the retry request. In that game, we would basically use the same I and the same J, but I would send the packet to J, and if it gets an acknowledgement, then it will not need to resend the packet, but if it doesn't get an acknowledgement, then it will resend the packet. The controller has to be aware of this ARQ capability and the loss ratio on the particular hop, so as to program enough time slots to get the kind of reliability we're after. In the terms of 6-dish architecture, there is a logical relation between those two time slots. It's a NOR logical representation. And that's basically my summary for what 6-dish would basically ask from PAR. Basically, use all the forms of diversities to improve the delivery ratio within the schedule time. And I'm listing here some forms of diversities that can be used for TSCH, but also for other radios. And so you have spatial diversity. You can build a track which is kind of complex with multiple paths and synchronization points, etc. So the track is not a serial list of nodes anymore. It's a very complex thing like a ladder or even a multi-level ladder. Beamforming and hoping different beams to use different reflections. That's a game that can be played. Time diversity with retries and time division. Frequency diversity, like we talked about the fact that 6-dish is not only using multiple channels, but also rotating them, and OFDMA, obviously. And then being able to schedule and exploit all those capabilities that I just discussed, like reflection, overhearing, interferences, etc. At the same time, as we want to use all that, we don't want to spend all the energy that would be necessary to exploit all the possible hops and all the possible beams, etc. So we want also to observe the quality of the links, use the best ones, and not waste energy and interfere by using the wrong ones. That's when there is all this need on OAM that I discussed earlier. Yes.
Just after you are done.
I'm done. That was my conclusion.
So, János Farkas, I'm hearing kind of quite some unfinished 6-dish work here, or that's the feeling I'm getting, and it could be done in 6-dish or finished in 6-dish.
Yes, that was an idea, right? Initially, for like 2 years, we thought, hey, let's push these requirements, and we have the 6-dish for .NET draft, which has been hanging out for like 2 years. And we basically expected some protocols to come out of .NET, which we could kind of add options to or something to do the 6-dish games. And well, for the one thing, it's not work which is high priority for .NET. To be clear, the wireless options would, like as was discussed in the working groups. Second is 6-dish is in the int area, and the crowd that was working on 6-dish was an IPv6 over foo crowd. So for this game, we want a more TCamp, .NET kind of crowd intermixed with radio people. So it seems that we need to change crowd. We need to, renew a bit our crowd. We need to maybe change area. And also, as we do that, and we work a lot on reusing work, which is done by CCamp, .NET, etc., it appears that focusing on a single radio, like was the charter of 6-dish, is no more right idea. We need to abstract that a little bit, 6-dish being one of those things we work for. And so all those reasons together tell me that, trying to extend 6-dish, stretch 6-dish all that way is probably not as good as just, forming a new group and saying, okay, here is how 6TiSCH saw it. Now let's form a group which can actually solve that. For 6TiSCH and for Wi-Fi and for whatever. Anything that can have those kind of same abstractions. And with this, we have Xavi on the mic and then Suresh. Xavi? Xavi?
Hello?
You were on the queue?
No, I'm not in the queue, sorry.
Oh, so, okay. So then Suresh?
Hey guys.
Yes, you
thanks.
well.
So Janos, you have a good point. So that's something I've talked to Pascal about. So right now, this is a non-working group forming BOF, just to explore the problem space and see what needs to get done, pretty much, right? So the actual way in which the problem gets solved is still open to interpretation. Is it going to be sitting in some current working group? Or is it going to be even a working group or a new working group? That all needs to be decided in the future. And I specifically don't want to spend time on it. Right? For today, my goal is to really understand, is there a problem to be solved and is there interest, right? And then we look at the actual dynamics. So this could be I want to make Loo jump, it could be done in .NET, for example, some part of the work. And we could start parceling this out to multiple groups, right? So that's something that we can discuss afterwards, not really right now. So my goal is to just figure out, is there something that needs to get done in the IETF? Go ahead, Lou.
Many thanks, Suresh. Lou?
Lou at the mic. I wasn't here originally for me, but I'll just, since Suresh said he doesn't want me to jump up, well, since I'm here, I'd actually say the 6TiSCH problem, particularly if you want distributed signaling, belongs squarely in CCamp. That they've done that a whole lot. So CCamp would be the right place. So not that. This is now for Meena Radhi. I'm curious for your thoughts on the feasibility of such optimization in a distributed hop-by-hop manner. So I guess it's on the previous one about maybe it's too late.
I didn't hear the question. I'm sorry.
I think they're looking for a discussion on the feasibility of optimization on a hop-by-hop 6TiSCH network. How feasible is it?
What we already did, I understand that it's what we already did, being able to schedule some cells based on the occupation of the air, etc. And we are on the way to produce RFCs for that, but I'm not sure it's the tight answer to the question. So mailing list. There's a PO mailing list, please. And with this, Georgios.
Hello, my name is George from EMT Atlantic, France, and I will present you the requirements of the packet replication and elimination that Pascal earlier presented. So I will skip some of my slides because I'm trying to say the same thing. So we have the wireless topology. S is the source, D is the destination, A and B are the relay devices. And then under such wireless topology, the replication will be when S transmits the data packet from S to A to its parent, and then he will replicate to its alternative parent to B. So this is the replication. And because we have too much duplication and unnecessary traffic, we will need to use what's called elimination to discard the copies of the previously received data packet. So this is the elimination. I will go faster with overhearing as well. So actually the idea here is when S as a source transmits to its parent A, because of thanks to the wireless medium, which is broadcast by nature, we may have this promiscuous overhearing and B may overhear this transmission. And like this, we will manage to increase the reliability in the network. And this is the simple example of the TSH schedule that we may have when we were using this topology where S transmits to A and B in parentheses will be the overhearing device. I will skip this and I will go to straight to the requirements. So actually, when we want to apply PRE in the wireless network like TSCH and replicate the routing layer, we are having some requirements to consider. And one of them is related to the alternative parent selection. So when we want to find the alternative parent, we should define over what kind of topology we are going to work. We may need to know whether we are having or not the ladder, how many parallel paths, what's the density, and so on. This is something that we may need to consider before. Then related to the routing protocol, it should allow for each device to have, in addition to its preferred or the default parent, what's called, to have a second one, an alternative parent. So we will manage to make this replication function. And then the third requirement for the alternative parent selection will be to, if we want to control the flooding, we will need to carefully select the alternative parent. And here I have a small example between the disjoint paths and the common ancestor. So in this example, if we are not carefully selecting the alternative parent, we may end up what we see here on the right figure, the disjoint. So we are having uncontrolled flooding, right? So this is unnecessary traffic, energy consumption, and so on. While if we are somehow controlling this parent selection, we may have this pattern, what we call common ancestor, where we will have two parallel paths that goes from the source to the destination. So here we somehow control the flooding. So these are the two examples. Then if we consider to go for the common ancestor pattern, then we may need to have some extra information so that we will select this alternative parent properly. So to do so, if we are working with Ripple and 60s, then we will have to extend the control packet. In this case, is the DIO as an example. Then the third requirement related to the promiscuous overhearing will be that the MAC implementation must support bypassing the MAC address filtering to accept the overheard frame. So meaning that in this example, when S will transmit to its parent A, at the MAC layer, we should allow that the B device should receive this packet by overhearing it. And then the fourth requirement, it is related to the packet elimination. So when we do all this replication, at a certain point, a device will receive multiple copies of the same data packet, and we will need to do this elimination. So to do so, we may need to consider to have an identifier. It can be sequence number, it can be timestamp, or there are many different ways to do it. So this we have to consider it as well. So that's it from the requirement. And then I will have some results. Pascal, do we have time to go through? Yeah? Quick.
1 minute.
1 minute. So here we will have different parents selection modes. So let's say this is the common ancestor, meaning that to select the alternative parent is the one having common ancestor with a default parent, so the preferred parent. So here we have three different modes, from the strict to the soft rules. And the more from the soft to the strict we go, the lower the probability to find this alternative parent. And more soft it is, we are having higher these chances, and which will reflect to our results that we have here based on this topology and these configurations. So the PDR here, you will see that we managed to have with packet replication and elimination similar results in terms of the PDR within the same slot frame. When I say within the same slot frame, this reflects to this nice figure, which is the delay and the jitter. Basically, as you can see, all three columns on the left, so strict CA, medium, and the soft, all of them, they are having this bounded delay. And if you see more carefully, we have the jitter, which is super low. So it's here. So this is because we managed to have correctly to bound the delay. So we have nice jitter, which you can see in the next figure in the top right. Well, that's it. And then this is the next figure that shows that there's a cost to pay, and the cost is that we have to traverse the packet through more devices, and we traverse through the more devices in this multi-hop wireless network. We are forwarding more packets. So we are working on this, how to improve this side effect of the PRE. We have the partial code is available already in the GitHub. We implement in Contiki. We have this wireless shark implementation as well. It's available. I'm not sure if you want guys to, we will push the results on GitHub repositories, or will be available for everyone.
Thank you, Georgios. So I'm sure you've realized, but compared to what's usual in the discussion we have around .NET and TSN and whatever, this is a distributed routing protocol we are talking about. We are talking about basically a ripple mesh with a root and some device. And what we are trying to achieve here is determine a track, automatically form a track, not just a sequential best shortest path, but a track from that device to the root to enable PRE over that track. And what is done is try to enable that you have at least alternates, but not too many to avoid flooding the whole network. So it's that control which is being discussed in this draft. So I don't know if we'll do distributed or if we can take this kind of work, but it's just to show the span of things which can happen.
Thank you.
So we're pretty much out of time. So we had in mind to discuss a little bit the charter which we want, but it's online and we'll discuss it. If you like, we'll republish this charter discussion after this call on the mailing list. And what I'm going to do simply now is, if I can, is announce something which is part of the discussion that we had with the ISG to enable this BOF today was that POW, useful as it is not a good idea for an IETF working group if ever we form one, because it's too close to POWs, which was something in white space, and I see Suresh is coming. And Suresh, I will give you the ball.
No, Pascal.
First time, Suresh.
Go ahead and finish up. I'll talk after.
Okay, so I got that button. Okay, so basically the idea is whatever we do from now after our discussion on the mailing list will not be called POW anymore. It's going to be called Spawn. So we actually spawned this working group from 6-net, CCamp. I mean, it's really about inheriting work from everywhere and extending it to our radios. And so that would be adding schedule in front of POW and networking in the end. And now the race is after a logo. So if you have any idea for a good logo for Spawn, then we're interested. And Suresh, whatever, ball is yours.
Okay, so personally, Pascal, right? I found like two things like of interest here that's work to do. So tell me if I'm off. Okay, one of them is like really like mainly OAM work. So like, doing the packet loss eval and like something that balances the resiliency versus like energy usage. That's one thing. And the other thing is some kind of signaling to do the POW flow, like with specific, spatial time and frequency constraints. So those are the two pieces of work I saw pretty much. And we really need to sit down and figure out like, how this gets done, right? So should this be a separate working group or not? So I understood your argument, like why it should be a working group, but I think that's something we still need to discuss. So can we just parcel off the work and do some kind of loose coordination? That's another possibility. So that's something we need to evaluate later. I thought we would have some time at the end of this meeting to do that, but we're out of time to do that. And I think we should continue discussing that before we lead up to Montreal. So we need something a little bit more specific and probably a little bit more socialized with the .NET, the TEAS folks and stuff like that, right? And so I think like Lou really had a good point when he talked about like, there's some stuff that's has like really homes in routing, right? So that's something we have to figure out probably offline to see is there a working group needed or not? And that's something we have quite a bit of time to do that. And that's something I want to focus on just to make sure that everybody understands the deliverables and see where they can be done.
Okay, Suresh, many thanks. And I guess we are past time, so it will be time to adjourn. I thank you all for coming and the remote presenters for presenting to us. I think that was great introduction to a number of those radio technologies. And for some of us, an interesting also view that wireless can be kind of strange in some days. So let's discuss more on the POW mailing list. A spawn will be created very soon. Probably the membership of PAR will be moved automatically. If it's not, I will signal to PO asking people to register to spawn, and we'll continue the discussion on the spawn mailing list. Thank you so much for being there today. Please send back the blue sheets towards the front.